Good evening, everyone. I'm Shafali Agarwal, and this is our eighth TA session on the topic of basic construction materials. So, as in last week, we have started about talking about metals in construction industries. Then we started from the iron, how iron is, how we get iron from ores, and how we are making steel, various percentage of carbon, how it is affecting the construction of steel, and then different type of rebars. We talked about uncoated steels in the last lecture, how we have different type of uncoated steel which can be ribbed or which can be plain. And so in this week, we will study about what are the different type of coated rebars, and then some uh, high strength rebars like pre-stressing steel, how we are using pre-stressed steels in construction for like mainly for bridges and high-rise buildings. And then what are the different test method and specification for steel or for any reinforcing bar when we are going to use it in the construction industry. So next thing is about the structure steel. So all these type of steels which will come under structure steels, and we will talk about two type of uh, metals except steel, that are aluminum and copper. So how these metals are formed, what are the properties, and what are their uses in construction industry or in general. So if we talk about coated rebars, the first type of coated rebars is fusion bonded epoxy coated rebar. So in this type of rebar, what we are doing, we are taking a normal steel rebar, a ribbed rebar, and then we are coating it with a epoxy. So if this is a cross section of a concrete system, so we have a steel, then we have this epoxy coating, and then we have concrete. So what this epoxy coating is doing, it is forming a layer over a steel bar. It is what we can say, it is just forming a layer over a steel bar which will prevent it to contact with the outside atmosphere. So how it is being formed is, first we will clean our rebars. Second step is it is passed through a machine where epoxy resin powder is ionized, and it is pasted on the steel rebar, or we can say through electrostatic force, it is being ionized on the rebars. And then we are doing water quenching so that whatever extra epoxy is there, it is removed, and there we have a plain rebar, sorry, uniform covering of our coating. And last step is to check for the damage or holidays. So what exactly holidays means? So from here, if you see, this is the same image of a normal epoxy coated rebar. So if there are any pinholes, like normally when we are doing any epoxy coating, you can see there are some gaps or bubbles formed over the rebar, over any coating. And when those gaps or those bubbles will burst, there will be a gap in the coating. So that is called as holidays in our coating. So usually in our rebars, you can see in our epoxy coated rebar, these type of holidays are very common. Uh, Unless and until you are having a very good production of your coating. If you are like pouring epoxy over the rebar in the multiple steps, or something else if you are doing, then we can say that our coating is very good. Otherwise, these type of they can be in nanometer also, not necessarily it is visible from naked eyes. So these small holidays can be there. And what will happen if these type of small holidays are there? So in this case, if you see, this is a scratch surface. However, there are chances of small holidays here. So what will happen, that small holiday will create a galvanic what is a connection. So what will happen, that rebar below this holiday or below this scratch, it will start behaving as an anode and will initiate corrosion without even the ingress of chlorides. Without even having chlorides, if you are having a rebar which have a damaged outer surface or damaged cross section, whether it is because of holidays or because of scratching or anything, if you have this kind of damage in this epoxy coated rebar, the corrosion will start even before the chlorides are getting into near the rebar surfaces. So what other type of disadvantages of this type of rebar is, when you are bending this rebar on site, you are actually damaging the coating at this end. So if you are bending it, there are chances that this end, that coating will be stretched and it will be burst, like it will be removed. And even during handling, when the rebars are taken from one place to another, because of harsh handling, there are chances that coating is removed. And when we are using this what we say damage coated rebars in our construction, again you will have a, so you will have a different kind of environment at this point and at this point, and it will create a galvanic type of corrosion. And another disadvantage is exposure to UV rays. So normally in UV rays, these type of coatings, what will happen? There are chances of melting and then they will get destroyed. So these are the main defects or disadvantages of epoxy coated rebar. So because of this, we will go to another type of rebar, that is cement polymer composite rebar. So that is called as CPC rebar. So again, this is another type of coated rebar in which we are coating it with the, we are having two layer of coating. First is CPC primer coat and second is CPC seal coat. So mainly this primer coat consists of cementitious material, and this seal coat is more of like epoxy. So we are having a cementitious coating initially. So what advantages cementitious coating will have? Main advantage of this cementitious coating is like it is providing an alkaline media over your rebar. So at higher pH, as we have studied before, at higher pH our rebar will be in passive state, and then we are providing a sealing over it, same way epoxy. So it have a double protective layer over our normal rebar. However, again, when we are handling it or when we are joining it on site, there are chances that because of rough and tough handling, this type of coating will get removed. And again, if the coating is removed, a galvanic cell is forming and you can have a preliminary corrosion even before chlorides are ingressing into it. So, this is another type of coated rebar. Next type of coated rebar is galvanized steel reinforcement. So these are the, what we say, inorganic coatings, or yeah, these are the inorganic coatings where we are using what is the epoxy or cementitious material to coat the rebars. Here what we are doing? We are doing a metallic coating. So over one metal, over steel, we are putting another metal, which is in our case zinc. So if we are using two metallic coating, what will happen? This outer metal or outer zinc will sacrifice itself to protect the inner rebar. So this is a typical process how this hot dipped galvanized rebars are formed. First cleaning, degreasing, rinsing, pickling, rinsing. So this all steps are of cleaning the rebar. Then it is put in the flux solution. So after putting in the flux solution, we will dry it and again we will dip it in the zinc bath and we will check the we will cool it down and check the coating thickness or if it is a proper coating, uniform coating or not. So this is how typical galvanic rebar look like, and this is a microstructure of galvanic rebar. So see, if because of this flux solution and when we are putting in zinc bath, at this point your temperature is very high, more than 700 degrees Celsius. So what will happen? Your rebar will be already hot, and when we are coating it with the zinc, so this layer in between, this interfacial layer of zinc and steel will have a content of both zinc and iron. So if you can see from here, we have a base steel where we have 100% of iron. Then we have a small gamma layer where we have 75% zinc and 25% iron. Same way as you go up, your zinc content will start decreasing and iron content will start decreasing, and at top you will have a layer of 100% zinc, which is called as eta layer. So this is how a typical hot dip galvanized steel rebar look like. So there is another type of galvanized rebar which is called as uh, cold galvanized rebar. So CDG, it is cold dip galvanized rebar. So in that case, your temperature is not high. So what will happen? Whatever layer you are forming, that will consist of 100% of zinc. Okay, there won't be any interfacial layer in that case. So that is another type of galvanized rebars which are currently being marketed. So this is how a cross section look like. This is your zinc and this is your zinc coating. So these are the different type of coated rebars. Next type of rebar is pre-stressing rebars. So where we are using these type of rebars is when we have a very heavy structure, when we require a lot of strength, mainly in bridges and all. So in that case, we will use pre-stressing steel strand. So a general pre-stressing steel strand consists of 7 wire strand. So if you can see here, this is how it look like. We have a sheathing, and that you will have a okay. This is a sheathing. In this you will have a different hose. No, this is for the complete. This is an anchorage. So this is for one strand, sorry, one rebar, you have 7 wire strand. So 6 at outer and one in between. So you have a in between this rebar is in this strand is called as king wire. So you have 7 strand wires and these are being packed using with a coating and inside a sheathing. So this is how typical strand look like. This is a 7 wire strand. This is how it look like. And this is a anchorage. So in bridges, we are not using a single uh, wire. Instead, we are using a full anchorage. So this is an anchorage. It is called as an anchorage. In that, you will have different small holes in from which you have different pre-stressing wire coming up. Okay. So these in general, when we are using in our bridges, we are using a 7 wire strand rebars, pre-stressing steel strand. So there are other different type of strands based on the application where you want to use or how much heavy your work is. You have a different kind of, you can have different type of pre-stressing strands. So few examples are like this. So these are like we have strand, then in between there are another strand, in between there is another strand, and then it is a combination of different strands or different pre-stressing steel strands, and they are combined to form another strand. So based on the application where you want to use it or how you want to use it, you can have different type of strands. So this is one another typical example. This is a 3 wire strands where only 3 wires we are using. So these are different type of pre-stressing strands. So this is overall overview of different type of rebars. So we have studied about in last week we have studied about plain rebar. Then we had ribbed rebar. Those were the uncoated rebars. And this week we read about the coated rebars where we started from the epoxy coated and then we have CRC coated and lastly we have galvanized coated rebars and last type of rebars are the pre-stressing strands. So next topic is about the different properties of your steel. So first thing is about the stress strain diagram. So normally what we are telling our steel is good in tension and weak in compression. So we will test our rebar for tension. When we are taking any rebar and we are putting in the tension, it won't have a what it's a brittle failure. It will always form a neck. There is a necking and then it will fail in a ductile manner. So this is a normal stress strain curve of your metals in tension. When this is a linear region, you reach yield strength. After yield strength, you have a plastic region, and then again you will have strain hardening, and that at last you will have the ultimate stress. And then after this ultimate stress, there is when cracks start forming, and we will have necking, and at a point this will fracture. So this is how typical stress strain curve look like for a steel material. And if this part is being highlighted, if you see this part, you can see proportional limit and yield stress are almost nearby. So this is a difference between proportional steel, from proportional limit and yield strength. So the point until which this is completely linear, it is called as proportional limit. So normally we are telling in elastic limit or up to yield strength, our Hooke's law is will follow. So actually our Hooke's law will be followed up to the proportional limit, and the strain, 0.2% strain from your what is a proportional limit at 2.2% strain, we will put a perpendicular line to this proportional line, and the point at which it is cutting our stress strain curve, that is called as your yield strength point. So that is the difference between proportional limit and yield strength. So these are the this is the basic stress strain curve for your metals in tension. Other thing is, what we have is high strength deformed steel rebars and their and wires. So normally in on site we are using Fe415 steel, Fe500 steel. So now comes the Fe415D, Fe415S. So these are the new type of rebar, or what we can say high strength rebar, 550D, and these are the high strength rebars which are currently being used for the, what we can say, high rise buildings, or where we have lot of load requirement. So in that cases we are using this high strength rebars. So this is what, these are the different properties of your rebars, and how with the strength parameter how these properties will change. So this all you might have studied in the lecture itself, so I won't go into details. So next thing is how different chemical ingredients will affect the properties of your rebar. So normally when we are talking about our steel, we are telling it is a combination of, it is a Fe, carbon, iron and carbon. So what exactly carbon is doing in your steel? It is providing hardness, strength, weldability and brittleness. And if you have a less than 0.1 carbon, it will reduce the strength, and if you have more than 0.3 carbon, it will make the steel more brittle. So generally we will have our carbon limit should be in between 0.1 and 0.3. Other thing, other additive in our iron is manganese. So addition of manganese will affect the yield strength of our property. Same way, sulfur will affect the brittleness, phosphorus affect the strength and brittleness, copper affect the strength and corrosion resistance, chromium affect the weldability and corrosion resistance, and carbon equivalent or Ce will affect the same hardness, tensile strength and weldability, same these three properties. So this is how different chemicals will affect the properties of your rebar. So next step is, what are the different tests we are being doing to check the properties of the you have any doubt, you can ask.
Ma'am, actually in assignment 7, they asked like adding carbon to steel reduce strength, whether it's true or false, like that they said.
Adding.
Carbon to steel
Hmm.
reduce strength, reduces its ductility and increases strength, like that they asked, ma'am. It
Adding.
is
Hmm.
adding carbon to iron reduces its ductility and hardness and increases ultimate strength, but it is decreased, right, ma'am, as per we discussed in that
Last
problem
lecture.
solving, and
Yeah.
also here also you were said strength will reduce it, but
Strength will reduce if it is less than 0.1 carbon.
they didn't say it like that, ma'am. They just
Okay.
said adding carbon to iron reduces its ductility and increases strength, ultimate strength.
Just in last week, there was one graph I think we have seen. Just 1 minute, I will open that thing. So if you can see my screen.
Yes, ma'am.
So actually that question based on this graph mainly. So they are telling if you are increasing the carbon percentage. So generally we want usually go beyond 3% of carbon percentage. If you have seen iron carbon phase diagram, so maximum is 3%. And in case of our steel, we are giving maximum 1.2%. So increasing carbon percentage is actually decreasing the ductility and increasing the strength.
Yes, ma'am.
Hmm.
In assignment, I said it is true, but answer they kept is false, ma'am. Adding
Oh,
carbon to iron reduces ductility and hardness and increases strength. It is true, right, ma'am?
no, no, no,
But
no.
in
But the hardness is increasing. In your
okay,
question, it was given hardness and ductility are reducing, but
okay,
hardness will increase.
okay, okay. Thank you, ma'am, for rectifying. Ma'am, one more doubt, ma'am. You said coating will be done for ripple bars, right, ma'am?
Coating will be done for ribbit bars. Yeah. In this case,
Can we done it for unripped bars? I mean plain bars. Coating can be done.
it can be done, but usually we won't use plain rebars in our what do you say in on site on in construction site mainly.
Okay,
So if you want to use it for something else, for what we say non-loading rebars, where like for balcony and all those area, then you can do coating.
okay. Thank you, ma'am, for rectifying. That's it, ma'am. Thank you.
So for the rebus, we are considering first test. As we have studied here, we will check the stress strain curve, or we will check the strength of our rebar. Second test is the bend and rebend test. So these rebend test is a modification of bending test. So we will check the bending capacity of our rebar. We will check if there are defects at this points, and we will check the defects, and we will check the capacity of your rebar to before it breaks. So that are the bend and rebend test. So this is all about iron or steel, or what we say rebars, which can be used for the construction. Other type of metals which are being used in the construction industry are the we will talk about two metals only, aluminum and copper. So first is the aluminum. So how aluminum is coming? We have a raw material called bauxite. From bauxite, we are producing aluminum. Bauxite will be gone to pressure. Then we will have alumina. From bauxite, we get alumina, and then this is the complete procedure you can see. And at the end of the day, you will get your molten aluminum. Okay, sorry. So the production of this aluminum from bauxite will have a waste material which is called as red mud. So this red mud have a very high pH and it is very dangerous. So there should be some what to say measures which can be done to reuse or recycle this red mud into our in any industry. So a current research is going on. Many researches are going on currently to use this red mud as an alternative to cement in concrete. So how this red mud can be used, that you can go through some journal papers. Many people have used red mud as a what they say supplementary cementitious material. So this aluminum, how it is being used in the construction industry is mainly for the electrical towers, or as in uh, scaffolding, or for instruments and all, or it can be used for the cladding or roof surfaces. So next thing about aluminum is how the stress strain behavior of aluminum look like. So if you remember about steel, it was like a, so at this point you will get yield strength, and at this point you will get ultimate strength. However, in case of aluminum, your stress strain curve will go always straight. You don't have this plasticity range area. You will have directly proportional limit, yield strength, and ultimate strength. So this is how an aluminum alloy stress strain curve look like. Other thing is how the strength is affected by temperature in case of aluminum, alumina. Aluminium, sorry. So if we increases temperature, the strength will decrease. So if we see our normal room temperature, at room temperature, if we have almost 300 kilopascal of strength, yield strength, then if we are reducing our temperature, if we go at negative temperature, our strength will actually increase little bit. However, if we are going higher at that room temperature, if we are heating up our metal, then our strength will decrease. However, if you can see at from this point to this point, it's almost linear. So there won't be a much difference in the yield strength of our aluminium. However, for the ultimate strength, the curve is much more, what we say, much more slopey. You have a bigger slope than yield strength in case of aluminium. So for aluminium, if you see, we do a procedure called as anodizing. So in anodizing, what we are doing, we are making the oxide layer stronger on the aluminium surface. So if this is our aluminium surface, we are providing power supply, and we are providing some cathode and anode, and this will create some hollow gaps in your aluminium surface, and this hollow gaps will be filled with the aluminium oxide further, and it can create some colors, if you can see here. So this is your aluminium surface, and then you are getting a aluminium oxide film which is created like this, and then these gaps, they are filled with the different metal deposit. Mainly in anodizing, we are filling it with the same metal. So if this is made of aluminium, we are filling with the same aluminium metal deposit. So if we are adding some pigments to it, you can make a colorful anodizing materials. So you might have seen aluminium water bottle, which are very colored, different colorful aluminium water bottles. So main procedure which is followed on those type of bottles is called as anodizing. Or if you have seen the non-stick cookers and all those things which are coming up nowadays for uh, new utensils, non-stick utensils, they will be of black color, nor it won't be of silver color as usual aluminium. It will be very shiny black color. So that all has been done by using the procedure of anodizing. Another procedure which is usually confused with anodizing, is electroplating. So main difference between these two are is, in electroplating, what we are doing, we are just putting a cover of another metal on our base metal. So in this case, in this base metal Me, we are putting a coating of copper. However, in anodizing, what we are doing, we are putting a coating of oxides of the same metal. So this is our aluminium. Then we are putting a coating of aluminium oxide, a strong oxide layer. We are forming a strong oxide layer over the rebar, over the, sorry, metal surface. So these are the things about aluminium. Another thing is copper. So in copper, not much things have been given in your lectures. So we are getting copper from sulfides, and if you see some famous structure like Statue of Liberty, it is made from copper. So why this green color is there? So oxide of copper is called as patina, which is a typical oxide layer of copper. So in iron or in steel, we have oxide layer of rust of brown color, and in case of copper, we have this green color oxide layer or rust layer, which is called as patina. Okay. So this is what you have studied in week 8. If you guys have any doubt, you can ask me now. Otherwise, we will go to problem solving session. In case of no doubts, then we'll go to the first question. quenching of epoxy coated rebars are necessary because otherwise, if we are not doing quenching, coating will evaporate, coating will harden faster, coating will flow down, or it will be a non-uniformly hardened coated. Any guesses? You can put in chat box also if you want. So quenching is the last procedure which we are doing. When our coating is being done, we will quench it with water. You remember this step. So this is the last step after coating is being done. We are quenching it with water. So why we are quenching it? The answer is C. If we are not quenching it properly, what will happen? This coating will flow down. So if this is a rebar and it is being coated with our epoxy, if we are not properly quenching it, this epoxy, it will be in powder form only, but this epoxy will start flowing down. Then you will have these kind of surfaces over your rebar. So this will create a non-uniform layer over the steel surface. So again, at this point, your coating thickness will be different, and this point coating difference thickness will be different. So to have a uniform coating, so that for have a uniform coating, we are quenching our epoxy coated rebar. Okay. Second question is, CPC coated rebars has a seal coat which consists of cement with fly ash, cement with bitumen, or cement with acrylic polymer, or just cement. So if this is a CPC coated rebars, we have three things. We have uncoated steel surface, then we are having primer coat, then seal coat. So we are telling seal coat will consist of what? So it is from here you can see this look like normal cement, but this look like it have some epoxy mixed to it or any polymer mixed to it. So it is neither fly ash nor bitumen. So it is a type of acrylic polymer. Answer is C. Okay. The third question is, which material typically shows a more distinct yield point in a stress strain curve? Aluminium, mild steel, copper, or brass? C. You are telling for this question or previous question? So we have studied about the stress strain curve of aluminium and mild steel mainly. So from these two options, what do you think which have a better distinct yield point? That is B. So this is a typical mild steel rebar. So if you remember in aluminum, we had this kind of curve. So this we were telling yield point, and this we were telling what to say ultimate point. So in this case, you cannot tell this curve doesn't show any plasticity. So you cannot define which is the yield point and which is the ultimate point. You can just say at the top point it is the ultimate point, but you don't have a defined yield point. So out of these two options, which will have a distinct yield point, it is mainly mild steel. Okay. Okay. From the similar question, compared to steel, aluminium has a well-defined yield point, higher Young's modulus, lower ductility, or lower yield strength. So these are the typical curves. Any idea? C. Okay. Lower ductility. C. Lower ductility. Actually, I don't have the ductility graph. So generally in aluminium, we have a higher ductility as compared to steel rebars. So I will just check the, I don't think I have. So generally, if we talk about ductility, it is more of the flexibility. So if you see from the practical point of view, we have more flexibility in aluminium as compared to steel. So actually, aluminium have a more ductility as compared to steel. So C is not the correct option. If you see from these two graph, normally in mild steel we have a yield stress of 250, right? And it can be 415 or 500, something like that. It depends on the what is the carbon content, what is the carbon content, or what are the different heating temperature or cooling temperature. Depending on that, you will have different yield strengths, but usually it comes in the range of hundreds. However, in this case, if you see in alumina, the yield strength is in the terms of 35 KSI. So in case of if we compare steel and aluminum, we have a lower yield strength as compared to steel. Aluminum have a lower yield strength as compared to steel. I don't have a diagram to show how ductility is affected, but uh, if you see ductility, it is compared with the flexibility. So if you see from practical point of view, aluminum have a higher flexibility as compared to steel, right? So the ductility of aluminum will always be greater than steel. But this is a pure case, pure aluminum. If you are adding some alloys to aluminum, again, it will change accordingly. Is it clear? So next question is fusion bonding of epoxy occurs at what temperature? 750 degrees Celsius, 500, 1000 or 200? So this you might have not studied in the lecture. So usually fusion bonding of epoxy happens at 200 degrees Celsius. Okay. Uh, Greater than 750 we are using for the galvanized rebar. For fusion bonding, we are putting it in the powdered epoxy we are pouring. So that happens at the temperature of 200 degrees Celsius. Next question is, holidays in the fusion bonded epoxy coated rebars can cause galvanic corrosion, underfilm corrosion, pitting corrosion, or uniform corrosion. So first we will try to understand what are the different type of these corrosion means. Galvanic corrosion means when you have different metal surfaces, like if there is a gap here and this is of different metal and this is of different metal, then that is called as galvanic corrosion because a cell is formed, a galvanic cell is formed. Next is the underfilm corrosion. Underfilm corrosion means means you have a coating which is destroyed and the rebar below which is exposed, and then you will have corrosion at this point, that is underfilm corrosion. Third is pitting corrosion. Pitting corrosion means due to the presence of chlorides, there is a pit forming into your rebar, and the same rebar is acting as anode and cathode. Last is uniform corrosion. So because of change in environment, that complete layer of your rebar is being affected, that is called as uniform corrosion. So from these four diagrams, it is clear that you have given the answer. Holidays will affect the have the underfilm corrosion. Correct. Next question is from the surface to the base steel, the zinc content in the layers of the coating in HDG steel rebars increases, decreases, remain constant. From the surface to base steel, zinc content is actually decreasing, right? From this point to this point, it's decreasing. Correct. So, eighth question is choose the correct statement or statements. Zinc is higher chloride threshold than steel. Zinc is higher pH threshold than steel. HTG rebars have higher corrosion resistance than uncoated steel. HTG rebars have a higher abrasion resistance than FBEC steel. The first thing is it have higher corrosion resistance. That's why we are telling our zinc will have a higher corrosion resistance than normal uncoated steel. How it is have a higher corrosion resistance? Because it will sacrifice itself instead as compared to the uncoated steel bar, which is directly exposed to the atmosphere. And other thing is it have higher abrasion resistance than fusion bonded coated rebars. So in this case, there is a chemically bonding between iron and zinc. You have metal and metal coating, and it will be much stronger than normal FBEC steel, where you have a just normal epoxy coating, which can be destroyed by normal bending or transportation itself. So it has a higher abrasion resistance, and this is also correct. Last two options are it has a higher chloride threshold than steel. Is it true or false? Any idea? So we will think from concrete point of view. From concrete point of view, zinc actually have a higher chloride threshold. It can corrode, that zinc layer will corrode at a higher chloride content as compared to the normal steel rebar. Last option is zinc has a higher pH threshold than the steel. So you just check the Pouvet diagram. I don't have here Pouvet diagram of both zinc and iron. So zinc usually have a diagram like this. So at higher pH than 13 or 12, it is in the corrosion state. However, our normal iron, this is for iron, this is for zinc. So normally in iron, our at higher pH of 13, our concrete is in stable state, or we can say a protective oxide film is formed on the iron surface. So the pH threshold of zinc is less than as compared to steel. So steel pH threshold is this 9 to 10, and zinc will be less than that, because at even at less point it is what is it? It can corrode. Okay, so correct statements are A, C, and D. So zinc doesn't have a higher pH threshold than steel. Zinc have a lower pH threshold than steel. Okay. So the next question is, dash are used in the railway sleepers. So we talked about different strand wires, 3 wire strand, 7 wire strand, or 12 wire strand. So in railway sleepers, we are usually using which type of strand? So this is our usual sleeper look like. So in this, we are using 3-wire strands for casting. Okay, is correct answer. Next question is, when initial cross-sectional area is used for the calculation of stress, it is known as nominal stress, true stress, initial stress, or actual stress. So when we are calculating stress, first stress is load upon area. So correct, A is the correct answer. So sorry, if we are using what is say final cross sectional area or cross sectional area after deformation here, then it is called as true stress. However, if we are using our initial cross sectional area, it is called as nominal stress. A, engineering, that is the same thing. You can call it as engineering stress also. Next question is, manganese content in the rebars affect the brittleness, yield strength, corrosion resistance, or hardness? So if you see this table, how if you are adding manganese to your iron, it will affect your yield strength. Okay, will it affect it in positive way or negative way? Any idea? So generally, if you are adding manganese to your steel or your iron, it will increases your yield strength. It usually increases the yield strength. Next question is, the byproduct from the aluminium manufacturing process with a very high pH is called as slag, lime, red mud, or iron. This we have seen in initial topic itself. The byproduct which we are getting from aluminium manufacturing process is called as red mud. Correct answer C. 13th question is, the process of coating the aluminium with a thick layer of aluminium oxide is called as aluminizing, electroplating, galvanizing, or anodizing. D, correct answer. So anodizing is the process when we are actually putting the we are making a strong or thicker layer of oxide film over the metal surface. In the production of aluminium, alumina is extracted from hematite, magnetite, bauxite, or rhyolite. See that. So bauxite is the raw material which is used for the production of aluminium, which is formed from the aluminium. 15th question is, what is the main purpose of anodizing? To deposit a metallic layer on the surface, to increase the thickness of natural oxide layer, to improve electrical conductivity, or to remove surface impurities. Mainly why we are doing anodizing is mainly anodizing is done to increase the thickness of natural oxide layer. B, correct option. Next question is, what is the key difference between anodizing and electroplating? Anodizing deposit metal, whereas electroplating forms an oxide layer. Anodizing uses the workpiece as the cathode, while electroplating uses it as anode. Electroplating deposit metal, anodizing form oxide layer. Electroplating increases oxidation, anodizing reduces oxidation. So we have talked about this in the initial choice slides. When we are doing anodizing, we are forming an oxide layer, and when we are doing electroplating, we are just depositing one metal onto the another metal. So answer is C. Okay. Next question is oxide layer of copper or bronze is generally termed as uh sorry, it's not generally termed as, it's generally called like, it's generally of what color? C. Okay, green, correct. So we are calling it as patina and it is of green color. So in civil engineering, where we are using aluminum as a RC structures, as window frames, roofing, foundation slab or brick wall. B, correct option, window frames and roofing. So for non-loading structures only, we are using aluminum. 19th question is the greenish patina on copper used in historical building and statues primarily consist of, or we can say, what is the oxide layer of copper usually made of? Copper hydroxide, copper chloride, copper carbonate, or copper sulfate? Yeah, the copper sulfate. So actually, this patina is made of sulfate. It is not, because copper comes from sulfides, but the oxide film formed on the copper, this patina, greenish patina, is not copper sulfate. Like generally, it is copper sulfate, but when we are talking about the historical building, it is made of copper carbonate. Copper carbonate is the correct answer. It is formed with the what we say, reaction of copper and CO2. It's not general oxide film which is formed in the copper. It's mainly with the time when copper reacts with the CO2, it will form copper carbonate. Okay. Last question is, how does zinc coating protect the steel rebar from corrosion? It forms a passive oxide film. It acts as a sacrificial anode. It increases the tensile strength of steel. It prevents oxygen from reaching the steel. So main function of zinc coating, why we are doing zinc coating is because it acts as a sacrificial anode. So at higher pH, what is happening? Zinc is getting used up, and it will protect your steel well. If you have a doubt, you can speak up or you can type your doubt here. Check assignment. Assignment 8 or 7? Let me know which assignment you are talking about. 8 or sorry, 7 or 8. This assignment you are talking about? Misunderstanding. Select one of the incorrect statement regarding stainless steel. What is your doubt in this question? So, if you can let me know what is your doubt, you can type your doubt. So, if I will explain why this is the correct answer, why excellent weldability is the correct answer. So, usually, if you know in stainless steel, we have chromium and nickel. So, if we are welding it, welding our stainless steel, what will happen? There is a chance due to heat, there is a chances of chromium carbide forming. Chromium can react and it can form chromium carbide, and it can weaken the weld point. That point can be weakened. So usually it have a good weldability, but it doesn't have a excellent weldability. So eighth assignment problem. Which question? These have 8 questions only. Can you tell the question number? Eighth question. The simply supported beam has a concentrated load at center W. The material A used for beam is steel and B is aluminium. Calculate the percentage increase in deflection in aluminium compared to steel. Do you want me to explain the answer? It's for past week. Oh, I'm sorry, I forgot to submit. I will submit today itself. So in that question, we have been given a normal simply supported beam, and it have a point load W at center. And then it is asked to us that we have two material being used for the beam. One is called a steel and another is aluminium. And what is given to us? Modulus of steel is given to us as 200 and modulus of aluminium is given to us as 50 GPa. And the question asks us calculate the percentage increase in the deflection in aluminium compared to steel. So if you have a simply supported beam with a point load at center, the equation for deflection is given as PL cube upon 48 EI, right? So your deflection, so we are telling this, we have two beams, one of made of steel and one is made of aluminium. So in this case, if we and both have been same loading. So from here, only values which is given to us is E. If you see P, load is same, length is same, I is same. So your deflection is actually inversely proportional to your E value. So now what is asked to us is percentage increase in deflection in aluminium compared to steel. So percentage increase in deflection of aluminium in compared to steel. So it will be this divided by steel divided by compared to steel. No? So steel into 100. This is what is asked from us. So you know deflection is inversely proportional to E, and this is the formula you have to use. Can you calculate it now? So this will give us, we will convert it into the form of E. It will be E of steel minus E of aluminum divided by E of aluminum into 100. So that will be a percentage increase in deflection. Is it clear? Okay. So I will post 6th, 7th, and 8th lecture today positively. And solve for this week. If you guys have any doubt, you can ask in the chat box. No doubts are there, then we will close the class for today. Thank you for joining.